Welcome everyone to hardwear.io webinar. Today we have Guillaume who's joined us for the webinar. Guillaume is a security engineer at Quarkslab, which is a French company specialized in information security research and development, consulting, and software development. He's mostly focused on hardware attacks on IoT devices, but also on reverse engineering and exploitation. He and his team at Quarkslab has organized the hardware CTF at hardwear.io since 2017. He's also a trainer of car hacking training, which was happening at hardwear.io Netherlands and Germany for the past few years. And today, Guillaume is going to talk about a tool which is designed to reverse engineer raw binary firmware called binbloom. So the presentation will take around 30 to 40 minutes, and you can ask your questions to Guillaume after the presentation. For this, please send your questions in the chat, either publicly for everyone, or you can also send Guillaume messages privately with the questions, and he will answer them after his presentation is over. So Guillaume, the stage is yours, please.
Okay. I'm gonna talk about automating firmware analysis today. I just would like to share part of my work, and I will explain you why. So my name is Guillaume. I'm co-head of the cryptographic and embedded team in Quarkslab, and as part of my job, I do security evaluations, and I especially work on ECUs, which are computers embedded in cars. And as part of this job, I often have the problem of analyzing raw binary firmwares. Okay, so the first time I had this kind of stuff to do, I was just stuck, like I think everybody else. And then I learned how to do it, and I see many people who are still stuck by doing this kind of thing. So I thought maybe it would be nice to share a few ideas to work on this kind of firmwares. So by firmware, I mean every single piece of code and data which you can find in embedded devices. Okay, it can be whatever you want, IP cameras, car, medical devices, whatever is an embedded device. So, okay, so for the agenda of today, I will explain the difference between reversing a raw binary firmware and other kind of firmwares, like the kind of firmwares you can find in embedded Linux systems with ELF programs and so on. Okay, so there is a big difference when you want to reverse a raw binary firmware. And then I will explain the tools I use and I've been using in specific missions for clients, in which I do an automatic pointer analysis, and it really helps. And we'll use this tool to do several things. The first and the main thing is to find the load address of a raw binary firmware. You can also find the base address, and you can find other little things like the endianness of the firmware, which is always good to know. And if you're lucky to work on a firmware coming from an ECU, I would like to share with you a way I used to start working on ECU firmwares. Okay, in the training I give for hardwear.io about car hacking and connected car hacking, I go into more details about loading the firmware and finding this kind of information. But I wanted to present this this work during the webinar. Okay, so sometimes we also called raw binary firmware. We also call them bare metal firmware. It's approximately the same thing. And so at first I thought, how hard can this be? I mean, just reversing, whether you are reversing an ELF or whatever, or raw binary firmware, just still reversing. Okay, so but no, in fact I was very wrong. It's very different to do that. Speaking about ECUs, do ECUs have a raw binary firmware? The answer is most of the time, yes. They do have raw binary firmware. More sophisticated ECUs like connected ECUs, most of them are split into parts. You have a legacy part which contains a raw binary firmware, and you have a more modern part with more connectivity, which in fact is most of the time an embedded Linux. So connected ECUs have both. Okay, so you see most of the time, at least in ECUs, you have raw binary firmware. In other devices like IP cameras, most of the time you have embedded Linux systems. But just loading, being able to load a firmware in IDA is not enough, because our job is to find vulnerabilities and to do security assessments on them. And once you've finished, you have to start all over again on different ECUs, different firmwares, and so on. So if you spend many days just trying to figure out how to load your firmware in IDA, well, it's not very effective. So let's speak about embedded Linux systems first. Okay, you can consider basically just like a PC. In fact, you have a microcontroller here, which is the equivalent of your CPU. You have a flash memory, which is equivalent to your SSD hard drive. You have, I don't know if this chip is RAM memory. Sometimes the RAM memory is inside the main chip. But, well, you have the same main components, and as for the inputs and the outputs, you have the same thing. Yeah, I mean, you have a power supply, you have USB ports, Ethernet ports, and this is specific to embedded devices. You can have GPIOs, SPI bus, or stuff like that. But globally, just like a PC. So what happens when you want to reverse a program from an embedded Linux system? Is very similar to doing reverse engineering on PC, okay? Because the programs here are in a specific format, which we call the ELF format. And in an ELF format, you have many metadata, meta information, which describe the program inside, okay? So what is the loading address? What are the exported and imported symbols? This kind of stuff, okay? And as it's dedicated to big systems, you will find also debug symbols, strings, and stuff like that. So I will just show you. So this is what you get in IDA in the end when you load an ELF. And in fact, I just loaded the binary from binbloom, the tool I'm going to present today. And you can find here that IDA has been able to find many function names, like the main function, or here the locate candidate database function. And here on the right pane, you can see the disassembly of the main function. Okay, so you just have to start your work here. You have the entry points and so on, so it's pretty easy. I will just try to show you a demonstration. If IDA is working correctly. So, yes. I'll just close that program. Okay, so when you start reversing a new program, which is packed in ELF formats, which is prepared in the ELF formats, you just load it, and IDA tells you, oh, it's an ELF 64 bits. And it's probably ARM or stuff like that. It will do everything by itself. And ta-da, that's all, okay? And you can see your functions here. You can find the main function, double click on it, and here I'm in the main function, and I can start reverse engineering this function and so on. Okay, so you see, it's pretty straightforward. So just for the comparison, and I will go into deeper details afterwards. When you try to load raw binary firmware, this is what happens. You that's all, okay? IDA tells you, I don't know what it is because it's not in ELF format. I have no metadata to describe it, okay? So I will go into further details afterwards, but you can see we are stuck right from the beginning. We have to choose many information like what is the architecture. I'll just show you if we select PowerPC big Endian. And then you are prompted with more information, which are typically present in the ELF header, like the start address, the RAM section address, the loading address, and so on. So I will just cancel the demo here, okay? Just to show you it's pretty different. Okay, so back to the presentation. Okay, when you want to start this kind of work, you have to know the architecture, because as I showed you, IDA does not know the architecture, it's not in the header, so you have to guess it by yourself. So you have several cases. Either you have physical access to your device, and I greatly advise you to just look at the, to open your box or your device and look at the writings on your CPU, okay? If you can do that, most of the time you'll know the architecture. If you can't do that, there are several tools you can use, like CPU rec. It's not, where's my mouse? Here, you can use CPU rec, you can use binwalk to try and identify the kind of assembly instructions you will have in your firmware. Okay, so here I'm running CPU rec on this firmware, on this file, and it tells you it's a Super H. A Super H architecture, so SH, maybe SH2, SH3, I don't know. If you start binwalk on another binary, it will tell you, oh, this binary is an ARM program in assembly mode. This is right here. And this is a bad guess, because as you can see in the name of the file, I renamed it. In fact, it's a Renesas V850 architecture. So you should be careful with these tools. That's why I say it's better just to read at the markings on CPU. So yeah, it works, but sometimes it doesn't. Okay. So back to IDA, you have to select the architecture you just guessed or read on your chip, and you can select it if possible. I said if possible because IDA is the tool I know of which is able to load the most who knows the most architectures. Okay, I mean there are other programs out there to do reverse engineering, like Guidra, Hopper, Binary Ninja, many others. But IDA is the most powerful for embedded devices. Okay, this is why I use it, but you can use basically any disassembler as you prefer. Okay, so here I select SH2 in IDA because I know my program is this architecture. And then that's where the bad news begins, in fact, because IDA is just telling you, you have been loading a binary file, and I don't know the entry points because there is no header. And so you have to figure them out by yourself, please. So you have to put the cursor where you think there is code, and press C to start the auto-analysis. The bad news is, basically, you don't know where the code is. And this is the whole thing about this presentation, how to find the code. If you continue and press OK, I will just try to find the code by myself. You are prompted with that. I mean, just a row, a big list of bytes here, and you have to figure by yourself where the code is. Sometimes just code, sometimes just data. You really don't know. So this is not really fun. Okay, I'm gonna just do a quick demo. Which is basically the rest of the previous one. Okay, so I will just select a binary here, and I know it's PowerPC Big Indian, okay? Because either it's written on it, or a friend told me, or I've been using CPU rec or stuff like that. So PowerPC Big Indian, it's here, set the CPU here. And I don't know the loading address. I will have to figure that out later. So I'll just say 0 for the moment. Then IDA says, okay, you're nice, but PPC, there can be many microcontrollers. Which one do you want? Here, I don't know, just say PowerPC. IDA tells us it's able to find many things like I/O, memory layout, and so on. So this is good news. Here we're prompted again with another question. Do I want 32-bit ISA only, VLE only, or mix of both? If you don't know, you have to try and guess, okay? Here, we'll say 32 bits. And here's the message I really don't like. You just loaded binary file, figure out by yourself what the code is, and good luck. And as you can see, you just have many bytes here, okay? Just big list of bytes. So if you don't know where the code is, you cannot work on that. So I will just do what Ida said. I will place my cursor somewhere and press C. And you see here, Ida says, make code fail. It means here it's not enough code. It's not possible to disassemble this byte. So you can try again somewhere else and still doesn't work. Oh, here it works. Okay, maybe I was lucky, maybe not. I don't know. It looks like code. Okay, it's nice, but really it's not a way of working. And as you can see later on, still some bytes. Okay, so do I have to start all over again? I can put my cursor here. Oh, it works. Okay, so really not a way of working like that. Okay, so what do most of us do is that they use the scripts, Python IDA scripts, to tag everything as code. So I will just do that right now. Go to script file and say tag code. Okay, and if I do that, I will just load a function which is called tag code. And this is kind of a brute force approach in which the script will go to every point and say, oh, this is maybe some code, and please create a function. Okay, this is what most of people do. This is what I do also from time to time, but I really don't like this approach because there is no. It's not very clever to do that. There is no meaning. You really don't know if the thing you are trying to decode as a function is code or is data, okay? IDA will try its best, but it really doesn't work very well, okay? Another thing we like to do, because it's an option of IDA, you go there in the option menu, in the analysis menu, and you click here on kernel 2 options, and click on make final analysis pass, okay? If you check this option, and then you click on the button here, IDA will try and use many heuristics. You can see it's working here. You can see the cursor progressing. And here IDA is just trying to use heuristics to determine what is code and what is data, okay? So it's a bit more clever than the script I just used before, but sometimes it doesn't work. Why? Because the guys who developed IDA did not develop those heuristics for all the architectures, okay? If you try a very common architecture like ARM or maybe PowerPC, stuff like that, you have chances that it will work. But for more exotic architecture like V850, stuff you find in automotive, most of the time it doesn't work, so you have to use this kind of script. So, okay, fine. I've been able to load my program, but I'm not really sure if the functions I found here are really meaningful or not. I mean, I just found them by brute forcing. So I'm not really happy with that. Okay, so that's the end for this demo. Back to the presentation. What do we do when we want to start reverse engineering such a raw binary firmware? There are common ways to do that work, and there are basically two ways of doing that. You can use a top-down approach or bottom-up approach. But if you use a bottom-up approach, you will base your analysis on very low-level facts and try to go upper and upper in the kernel, in the middleware, and the application layers, and so on. So, for example, the things you can use are the interrupt vectors. This is something we use very often, like the reset vector, the can reception vector, and so on. What are those vectors? Those are interrupt vectors, which are automatically called in case of an external event. For example, if you reset your microcontroller, it will start its execution all over again from the reset vector, okay, which is a fixed or specified 32-bit value. If you receive a can message, your microcontroller will get an interrupt and it will start executing the code at another specific address. If you know this address, you can start reverse engineering your firmware by saying, okay, what happens when I receive a can message? I go there. So this must be somewhere in the can driver, and from there from there you can go, you can follow the cross-references and go to the kernel, for example, or to the on the operating system, and from there you can analyze the middleware and the application and so on. It's a huge work. It's not the thing I prefer to do. Okay. Another thing you can do, and this one is a bottom-up approach, is to use high-level features like strings. It can be error messages. It can be information. It can be many, many things. You can also ask yourself about the known features of your firmware, because I mean, if you're reverse engineering a firmware from a car, it will not behave in the same way as a firmware from, let's say, a washing machine. Okay, they don't do the same job. So what is the job exactly of an ECU? You can ask yourself this question, and from there you can find out specific behaviors or communication protocols or stuff like that. So this is the top-down approach, which I really prefer. For the bottom-up approach, this is the, I wanted to present what I use here. It's based on the memory map. So what is a memory map? For a microcontroller, it's the fact that everything is organized in the same address space. So on 32-bit microcontrollers, the address space is 4 gigabytes, which is pretty much. In fact, you don't have 4 gigabytes of memory inside a microcontroller. You have a few megabytes of flash memory, a few kilobytes of RAM, and other stuff for IOs. Okay, so here you can see on the schematic taken from the datasheet. That's the internal ROM area is located here from 000 to 00 FFFF. Okay, the RAM is located here from 03FF 000 to 03FFE, blah, blah, blah. So what does it mean? It means, well, when you read an absolute value, an absolute pointer, just looking at the beginning of the pointer is enough to tell you if it's a pointer to the flash, to the RAM, okay? And this is exactly what I use here. I will, the tool I'm going to present today is called binbloom. And binbloom, in fact, what does it do? It's just reading the whole firmware memory, and it will split, according to the size of the firmware, it will split each 32 bits value inside two parts, a prefix part, which is supposed to be constant, and a suffix part, which is specific for each pointer, okay? So what does it mean? It means if your memory space is 64 kilobytes, 64 is represented on 16 bits, right? So if you have a 32 value, the prefix is 32 minus 16, so it's 16, okay? So if your memory space is, if your firmware size is 64 kilobytes, you can expect to have 16 bits, which are always constants for the flash memory, okay? If your firmware is 1 megabyte, you need 20 bits. So the remainder bits are 12 bits. So you can expect to have 3 digits, which is the same as 12 bits for the prefix, okay? It means just by knowing the size of the firmware, you can determine the size of the prefix. And if you know the size of the prefix, you can brute force all possible 32-bit values in your firmware and put them in the right buckets. Okay, you just look at the first digits, you compute the bucket, and you put the rest into this bucket. So just basic statistics, you know. So what's the result from that? The result is that if you analyze the firmware like that, and you count the number of unique pointers inside each bucket, you will see that some buckets contain more values than other buckets. Here, for example, the first bucket, starting with 000, contains 1600 values. Okay, this other bucket, starting with 0B4, contains 2100 values. And the last bucket, starting with FFF, contains 2900 values. All the others contain less values. So what does it mean? It's not by chance. I mean, it really means something. What does it mean? It means that you have many values starting with the same prefix, obviously, but we still don't know if how it's usable. Okay. So this is what I'm going to show right here. A fun side effect is that just doing the statistic analysis, the program was able to find other areas in memory I did not know of. Most of the time, I'm most interested in the flash memory, but this program showed me other areas of interest like EEPROM, RAM, peripherals, and so on. So it was, yeah, it was just fun to see that as a side effect. It's not directly usable like that. You will get information, but it's not enough to be very useful. Okay, so what do you need more? I'm using this program, for example, to make the first analysis, which is analysis of the endianness of the microcontroller. What is the endianness? It's the way you store big values into a series of bytes. The memory inside a microcontroller is basically a series of bytes, but if you want to store 32-bit values, which contains 4 bytes, you will have 2 ways of storing it. In the natural order, I mean, if your 32-bit value is 1, 2, 3, 4, you can store it like that, 1, 2, 3, 4. It's what we call the big endian mode. But you can also store it in reverse order, like 4, 3, 2, 1. It's the little endian mode. So, if you remember, I said the prefix would be common amongst all the pointers because of the memory map, okay, because of the way it's organized. So if you start the same analysis in big endian mode and in little endian mode, which is just by changing the way the 32-bit values are read in memory, you will get different affectation to buckets, okay? So if I do that, for example, on specific firmware, you can see if I read 32-bit values as big endian, you will see we have just 2 here main buckets in which we have high number of unique pointers. Okay, if I do the same analysis in little endian, we'll have completely different numbers here. Okay, another heuristics I introduce in this tool is not only the number of unique pointers, but also the number of pointer which are presented as elements in an array. Okay, why is that? Because I was looking for more information, more specific information, and just taking random 32-bit values here and there in the firmware was not really meaningful. I thought maybe it would be more meaningful if I have a succession of many 32-bit values starting all with the same prefix. It cannot be by chance. If they all follow themselves in the same order and they all have the same prefix, it must mean something. So it can still be data, function, a pointer function, pointer to whatever you want, but it's more meaningful. Okay, so this is what I did here. And you can see if you make a sum, so we won't consider here the number of unique pointers, we'll just consider the number of elements in potential arrays, okay? And if you make the sum of all those elements, you have the sum right here and right here. You can see here we have like 800,000 potential array elements, and here we have 4 millions potential array elements. So it's a clear indication that we found much more, a bigger correlation in the prefixes when using the little endian mode. So we'll say this firmware is a little endian, right? Okay, but is it really useful? I mean, we know we have a sequence of values with the same prefix, that's fine. But how do you distinguish between raw data and functions and pointer to functions or pointer to data? Well, you don't know because there is no information as to what each 32-bit value corresponds to, okay? So is it enough to find the raw base address? Yes, it is, because you can just check the buckets with a high count of elements. For example, here, the bucket starting with 000 is a good candidate. Maybe it's a false positive because most of the time the raw data on 32 bits are lower than 32 bits, so they all start with 000. So be careful with the bucket starting with 000. Sometimes it's a false positive. So you have to look for the other ones. So here, this one is also interesting. And maybe the base address is something looking like that. So F88, okay, and 000. But is it enough also to find the precise loading address? No, it's not. Because doing that is just raw statistics. You basically know where your code is located, but you don't know much. What's the difference between a base address and a loading address? Difference is that if you get the firmware here, maybe you don't know, maybe there is something else just before. So for example, if your base address is 0, I mean, your code start at 0, the flash start at 0, maybe you have a bootloader first or something else, you don't know, and maybe your firmware starts at a higher address. So here the loading address would be this value, the size of bootloader, and the base address would be that. So are these heuristics enough to determine the loading address? No, and it's sad because this is exactly what I want. So what should we do? Basically, in an ideal world, we would know the address of the functions, okay? And if we know the address of each function, we are also able to look for 32-bit values inside arrays, inside the firmware, and do a correlation between those two, okay? It's a bit of a chicken and egg problem because obviously to load the firmware at the correct address, to have this representation at the correct address, you have to know the loading address. So if you don't know the loading address, you can't get the precise address of the functions, and you can't make any correlation between the 32-bit values here inside the firmware and the address of the functions because you don't know the address of the functions. So one way of breaking this chicken and egg problem is to consider that you will force the loading of your firmware at address 0. And then what can you do? You can just look at the offsets of the functions here and say, okay, if I consider maybe this 32-bit value, it corresponds to any possible function starting at offset 0. Okay, let's say it corresponds to this one. So let's forget about the 800 here. It corresponds to this value. If you do that, you will compute an offset, which is in fact the loading address. And if you do that, and you make an assumption on the loading address based just on one couple of 32-bit value and a specific function inside the firmware, you can check if you find correlation for all the other 32-bit values of your array. Okay, so it's based on an assumption and a correlation. So basic statistic here all over again. So what do? We need to get a list of potential functions, and this is something we know how to do. This is exactly what I did in the previous demonstration, just by loading the firmware in IDA at address 0, using the tag code function to analyze all possible functions with possible false positive, but we don't care basically, and we'll save that to a file, okay? And then we will use binbloom to make the correlation between those possible function addresses and all possible arrays containing function pointers. Okay, so obviously it's a lot of computation, takes a lot of time, but it works. Here is the results. On this firmware, binbloom has been able to find a correlation on 968 functions based on the assumption that the firmware was loaded at this specific address, 9F0000. Okay, so it's pretty high number of functions, cannot be by chance, and it means this is the loading address. And if you use this address in IDA, everything will just match. Okay. Then binbloom is just exporting the address of all pointers, and of the 968 function it has been able to discover. And you remember when IDA was saying, please put your cursor in a specific place and press C? Well, then there is one script here to import all this. And in fact, what we will do is use the 968 locations to start an auto-analysis, and not just one. So the results are much better. I will do a demonstration just after, because I think I'm running a little bit out of time, and I will test the demo afterwards, right? So the last part of binbloom is the part which is specific to the ECUs. Okay, an ECU firmware obviously has to contain specific information about the behavior of the ECU, and most of the time ECUs speak communication protocol on the CAN bus. It can be UDS or KWP 2000. It can be different kind of communication protocols. Here I will take the example of UDS, of the UDS protocol. Basically, UDS communication contains a service identifier, which is basically a command number, and that's all. And it contains also parameters. But basically, the most important part is the service identifier. So what happens, for example, when you go to the car mechanics, it will just, and you want to know if there is a problem with your car, it will just send a command to read the DTC information. DTC is diagnostic trouble code, and which is in fact the errors which are stored in the ECU. What does it mean? It means that if you send the value 19 to an ECU, the ECU will respond with the list of the actual defaults. Okay. So there must be some place in the code where this list of values is hard-coded. Okay. If you look for this, an array containing these values, you will get good surprise. You will get something like this. This is what binbloom is doing for the second part, scanning for what we call a UDS database. It will look for arrays in memory in which the first column is only UDS values, UDS commands. If you do that, it's very powerful because most of the time, if you're lucky, you will find also a function pointer right behind it. Okay, so what does it mean? It means that to execute the command number 10 in UDS, the code will just jump to this address. If you want to execute command 27, the code will jump to this address. Why is it interesting? Because if you're doing security evaluations on ECUs, you want to look for specific information, like the function, the UDS function 27, which is called security access. Okay, the security access is the main entry point in case you want to download the firmware, upload the firmware, do advanced stuff. Okay, so this is a good target for hackers. And so when you do security evaluation, you want to review this function. So you have two options. Either you use a bottom-up approach starting from the can-rx interrupt vector and work your way up to this function, or you are able to find this function directly. Okay, if you use binbloom and you are lucky enough to find the UDS database, you can directly have the address of the UDS function responsible for the 27 service. Okay, which is pretty interesting. So let's do that. You see the address here is 0A8A-EC. So we go there in AIDA and rename this function as UDS service number 10. Okay. If you go back to the next one, you see the address is the one I said just before, 0A8A-EC. So you go there in AIDA again, and you see there is no coincidence. It's right where the previous function stopped, because AIDA was not able to continue its disassembly. So you go there and you press C here, and it will continue and disassemble this function, and you can just rename it service 27. Okay, so just by doing that, either the previous mode of importing all the discovered functions, or just by looking for the raw CAN database, UDS database, sorry, you can find the main entry points. Okay, so I will just do a demonstration to finish this presentation. I'm currently finishing the open sourcing of binbloom. I've been announcing it since a few months now. I had to fix a few bugs and write the documentation and so on. So I still had to write a few information in the documentation, but basically it's done, the code is clean. So I expect to open source this program next week. I will make an announcement on Twitter, so you can follow me if you want to be updated on that. Okay. As a conclusion before the demonstration, just loading a raw binary firmware can be a very time-consuming task, and it's really important to be able to automate this process. I've been stuck very often in this kind of analysis. This is why I wrote this tool, and I wanted to share it with you. because there are many other tools which helped me, like binwalk or cpurec and so on. I just wanted to be part of that. If you have any feedback or whatever, please don't hesitate to share it with me. Okay, thank you. I will just do a few demonstrations if I have the time. I will do two kind of demo. One in a working case. I won't do this one because it's pretty long, but I have the log. I can show you the log if you're interested. And I will show you also in a non-working case because, as I explained before, binbloom is based on heuristics, and heuristics don't work all the time. Okay, for example, for this specific firmware, I suspect there is a compilation option which makes sure that there is no 32-bit pointer to functions. Okay, or maybe the firmware is a multi-part firmware, and I just have a look. I can just examine, inspect a very small portion of it. Or maybe you have something where you also have sometimes in the embedded world, which is called mirror segments, and the prefix can be different, but the content is the same. Anyway, sometimes it doesn't work. Sometimes it works very well. Sometimes you can find the UDS database. Sometimes you don't. But I'm releasing this program because well, most of the time it works. So I think it's worth sharing. I will just do a small demo right now for NEC Renesas V850 E2 firmware I got from friends. So you can see that using cpurec is making an educated guess. I mean, it's correct. So you can just start IDA and say, okay, we'll just look at this firmware right now. Okay. So NEC Renesas blah blah blah. It's this one. Here you have to select the correct architecture. NEC starts with an N. V850 E2. You can see this one here. Choose the correct microcontroller. And as I explained before, you don't know the loading address at first. So you will just select 0 as the loading address. Warnings. And go find yourself the starting points. Thank you, Ida. And here you are. Okay, you see here everything is brown. It means everything is just raw data. Okay, so we'll just start our script tag code. It will take a few seconds. It's not too long. We'll wait for the end of the auto analysis. And after that, the script will save all the functions it has been able to find right here. Okay, so you don't need to do anything else here. We'll just close this database and don't save it because I know the loading address is not correct. Most of the time it's not correct. So now we can use binbloom. And we'll specify this firmware and ask for, you can ask for several things. You can ask for an endianness analysis with the -E option, and it will use its heuristics in big endian mode and in little endian mode. Okay, so here you can see in big endian you have many buckets but with low counts. Okay, but in big endian, in little endian mode, you have a higher count for just one bucket. Okay, this higher count means that this was the correct option. So binbloom is telling us this program is in fact a little endian program. Now I will use the -B to ask for analysis, an analysis of the base of the loading address, of the base address. It will start again by doing the endianness analysis because the endianness analysis is needed in order to be able to compute meaningful candidates for the base address and for the loading address. So here, what it's doing? It's just trying to find all possible arrays containing 32-bit values. And in an array, if I come back here, you can see here there are many bytes in between two consecutive pointers here. Okay, you have 4 here and 4 here. So here the stride would be 12. Okay, if you consider the UDS scan database, it means the stride is the number of bytes you have to skip between two UDS consecutive values, and it's 12 here. But if you just consider the pointers, the stride is 8. So binbloom cannot know the possible stride before this analysis, so it has to try all of them. Okay, so this is what we do here between the stride of 4 and stride of 16, and boom, it works. So binbloom has been able to find here the loading address, the base address, and amongst the 6,000 functions we found by brute forcing the firmware with IDA, 1,200 of them were matched with specific locations in the firmware. Okay, so it's pretty good results, in fact. So once the base address is known, binbloom is doing the analysis over again, but in a different way, just by saying, okay, do the same work, please. But each time you find a function for which the loading address would be this one, please just save it in file, okay? And this is the file I'm just gonna use right now. You see, binbloom is just finishing its analysis. So I will load the binary again, the firmware again, using, so we say it was NEC, Renaissance, blah, 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 V850. Okay, but now we know the loading address. Okay, it's this one. It's E with 3 zeros behind. Okay, and if I do that in between, binbloom finished creating the export files, and we can just use another Python script to import those entry points. We'll go to the correct folder, and it was NEC Renaissance, it was this one. And for the pointers themselves, I will use the FPT file. And you see here, in this task, in this bar, IDA has been able to find most of the functions. I mean, we have, instead of having just one entry point, we have 1,200 entry points now, which gives a much better result. And if you want to finish your work, just go to Options, General, Analysis, check this make file analysis pass, you analyze the program, and here IDA will use those new functions as entry points and start the analysis all over again and find all possible code. Okay, it's not completely finished, but most of the work is done, and you can really start working on that. I said it's not completely finished because, as you can see, in some places you have code which is not tied as functions. You can do that, but you see here you have no cross-ref. As you have no cross-ref, you can say it's a function or not. You don't care. Well, that's all for this demonstration. Thank you for staying to this webinar, and I hope it was interesting for you. I will just look at the questions now if you have some.
Yeah, thank you, Guillaume, for your presentation. Yeah, please, everyone, send your questions to Guillaume. He will answer them now. We have a little bit of time left, so let's say 2-3 questions Guillaume can answer. You can check in the chat.
Okay.
If you got questions.
Yeah, I'm just reading them. The first one are about publishing the webinar on YouTube. When and where will the tool be available? So it will be published on the GitHub of my company, which is Quarkslab. And for when, I expect it to be published on next week, because I consider the code to be almost presentable. So it should be okay. So next week on Quarkslab's GitHub. And if you want, you can, I will make an announcement on Twitter. Which architecture does it support? It's a very good question. And basically, it's completely architecture agnostic. I mean, it can support any architecture because it's just doing statistics on the raw binary. For specific features like UDS database, it's completely architecture agnostic. For other functions like finding the loading address, as I showed, you have to create a list of functions, of possible functions. You can do it with any tool. In fact, just a file containing offset of functions in hexadecimal, so very, very easy to produce. And you can use any reverse engineering tool to do that. So I would say binbloom supports any reverse engineering tool able to produce a list of functions, of potential function for a firmware. So the next question is, what are the heuristics that you input for your program? The heuristics are just checking if a 32-bit value has the same prefix of another one, okay? And starting from that, you start making correlations between two 32-bit values and say, oh, those 32-bit values have the same prefix. And they are spaced by, let's say, A bytes. And let's look a byte further. And if a byte further, you have another 32-bit value which has the same prefix, well, it does mean something most of the time. So this is the only heuristic I'm using for the UDS database analysis, for the endianness analysis, and for the loading address analysis. I'm also using the fact that you must have this kind of correlation, and it must also correspond to other functions which are specified in the external file, the functions file.
Okay, we have say one more question. And
yeah, one more question. What do you do if there is no support for the firmware architecture in IDA Pro? Well, that's a good question. You can check online on GitHub or other software repository, because IDA Pro or for that matter, Guidra or probably other tools are able to support other architecture. For example, yeah, last year I had to make a security analysis for a V850 ECU, and at that time this architecture was not supported in IDA. But luckily enough, a guy, I don't remember his name, but this guy made a plugin called neckromancer.py to analyze V850 firmware. So I would advise you to look online if there is a plugin for IDA or for Guidra to reverse the architecture you want to use. And honestly, if you have no support for this architecture in any tool, you can start writing your own plugin. I was said it was not so hard, but I never did it myself, and I consider it maybe not so trivial to do it. But it's in fact your last chance to work on an architecture which is not supported by those tools.
okay, thank you very much, Guillaume, for your presentation, coming to the webinar.
Thank you for having me.
Always nice to have you at hardwear.io. And few announcements before we finish from outside. Next webinar will happen on 11 June on Thursday, same time at 3 p.m. And Ferdinand Noscher will speak about analyzing embedded systems the smart way. There is a link in chat now that you can register for the next webinar. And thank you everyone for joining.